Good morning, everybody. My name is Viluethapad. This research was made possible under my mentor, Dr. Clough. He is with the Biomedical Engineering Department here on campus, and we did research to validate a open circuit resonance sensor as a proximity patch. So before we get into the body of the presentation, it's important to go over some key terms. So EVA specifically stands for extravehicular activity, which is defined as any activity that takes place outside of spacecraft. Next is the EMU, which is the extravehicular mobility unit. Also known as a spacesuit, it provides communication, mobility, and protects the astronaut from the harsh environments of space. And specifically on the EMU, that's important, is the hard upper torso, or HUT, as I'll refer to it from here on. It is a rigid body that the modular limbs of the spacesuit attach to. So even though NASA has developed insane technology over the years, the design of the spacesuit has essentially remained the same, consisting of a hard upper torso and attachable limbs. And even though the spacesuit design is structurally sound, since it rests on the shoulder, it's a heavy garment that rests on the shoulders, it can cause irritation at the rotator cuff. So with this technology, we hope to eventually create a patch that can quantify fit and comfort. So here is the hard upper torso, and that's how it fits without all the other components attached to it. And because of this design, astronauts are biomechanically restricted within the suit itself. So it's similar to if you're wearing a suit that's too tight around the shoulders and you can't raise your arms too far. And in fact, the shoulder is actually the second highest reported area of pain following EVA training. So there are limited methods that exist currently to quantify comfort and fit within the EMU. So we're trying to use NASA-developed technology, SANS-EC Tech, to create a patch that provides data within these suits in real time. Currently, this technology is used to detect lightning and damage detection, changes in fluid level volumes in rocket tanks, and temperature and volume changes. And this sensor in particular is ideal for its simple design, low cost to manufacture, and reliable readings that it can produce. And eventually, with all of this data and this technology, we hope to develop a more mobile spacesuit and overall reduce training injuries that are caused from the EMU. So for this study in particular, we decided to use a square spiral planar pattern. We used a click and cut process, which is similar to a Cricut machine. And here's the sensor itself that we ended up using. All right. So the sensor acts as an antenna that measures changes in the environment. So, and specifically according to Lenz's law, when an object interacts with the sensor, it induces a current to create a magnetic field. This magnetic field is emitted and then returned back to the sensor. And these reflections are called S11 reflections, which are what we use to quantify these changes in the environment. So to validate this, we created a gel-like phantom that consisted of cross-linked formaldehyde to mimic the dielectric properties or the skin response to the sensor. And we tested this at a frequency range of 1.2 to 1.4 gigahertz. And the sensor remained fixed while the gel substrate was placed on a stage controlled by a micrometer and moved towards the sensor from a range of 0 to 2 inches. This data was further analyzed with a two-way ANOVA, and multiple comparisons of means in order to differentiate that each increment is providing significant data. So this is the S11 response that we gathered, and here is the response at 2 inches, and as it moves closer, this is called a principal resonant peak frequency. You can see that these peaks increase in height as we move closer to the substrate. So this data was then plotted The frequency data was then plotted against displacement, as seen here. And unfortunately, we didn't see a totally linear relationship. However, since we did the two-way ANOVA and the multiple comparisons of means test, we could say that each incremental distance was significant on its own, and that we could correlate specific peak frequencies to these distances despite this lack of a linear relationship, which means that in the future, we just need to make a better sensor design. So essentially what that means on the last slide, is that every single time we hit 1.3 gigahertz, this correlates to zero displacement, which is the shoulder making contact with the hut. And like I said, the more contact we make with the hut, the more chances increase of injury. So there were quite a few limitations to this study. Considering the fact that we didn't get a linear plot, we decided it wasn't viable to do a linear regression quite yet until we came up with a better sensor design to create a more linear relationship between the two variables. In addition, we would like to test more setups. So in this case, we had the sensor fixed with the substrate moving, and we'd like to reverse that and to simulate the idea of having the patch on the skin and having it measure the suit from there. In addition, there is a possibility of undesirable coupling because it could be picking up extra signals from the additional layers of biological tissue underneath. So in addition to the skin response, it could also be picking up muscle and fat and biological fluids. And in the future, when we do repeat this study, we'd also like to decrease the testing range from 2 inches down to 1.5 centimeters in order to simulate the environment of the hut being on the astronaut, because the general clearance is about 1 centimeter. And hopefully, with all of this, we can eventually work with Johnson Space Center to test the EMU to develop better spacesuits. So to reiterate, there is some evidence of relationship between frequency and displacement. And we can use this to increase comfort and therefore decrease costs for injury care and/or treatment afterwards. And our sensor is ideal for this application because of its simple design and ease of application to provide high resolution feedback in real time. And it's easily manufactured in low weight, which is ideal if this technology is ever used in space itself, since it's very expensive to send additional mass into space. So in conclusion, since the EMU will retire alongside the International Space Station in 2024, it's very important that we take a critical look at comfort within the spacesuit to develop better ones in the future. And this sensor can be used regardless of what design NASA decides on in the future. And so as we prepare for our missions, as our missions evolve to venture into deeper space, these examinations of comfort is vital for the future success of manned missions. All right. I would like to thank Dr. Kim Clough and the McNair program for making this research possible, and NASA for, in part, funding this research along with Wichita State. My lab partners, Reese, Bernardo, Jacob, and Ryan, who were fundamental in my understanding for this project, and my family and friends for letting me willingly enter insanity within reason. All right, here are my references.